going on this vocab, let's go ahead and look at an example. What? Let's go ahead and look at an example. So wherever you left off in your notes, let's go ahead and, in a sense, summarize what the situation is as an example. I know it's going to be out of order, but it's actually going to be perfect to what we're covering today. So what is the... All right, test put away, corrections put away. We'll have more chances later. Set the scene. Every probability problem, there is a scene. Set the scene if you've ever taken drama. Set the scene. What's going on? 8 pieces of paper, all of them numbered 1 through 8, in a box. You draw one piece of paper at random from the box, record its number, and put it right back in. Then you draw a second piece of paper at random from the box and record its number. Finally, you add the two numbers. How many different ways can you obtain a sum of 12?
3.
3?
Oh, technically 6.
Technically 6? What are you guys thinking? Sum of 12. Hold on. 1 and 12 would make 13. That's not good. And we only have numbers 1 through... So hold on. Give me something that does... No. What's something that works? 4 and 8? That works. 5 and 10. 10's too big, right? 5 and 7. Those work. 6 and 6, except there's only...
No, except you can replace.
But you can, good. There's only 1 6, but you put it back, so maybe you get it again. Ten's too big, bud. Just 1 through 8. So anything else? Because 1 needs 11, don't have that. 2 needs 10, don't have that. 3 needs 9, don't have that. I only have 1 through 8. 4 needs 8, or 8 could go with 4. 5 needs 7, or 7 could go with 5. 6 needs 6, and, well, either way, you're getting the same piece of paper. Right? So how many ways is it possible? 5. How'd you get that answer?
There is 5 pairs.
You found the 5 pairs. Yeah. You identified exactly the ones that work. True? What if I was to ask you something else? What if I was to ask you another question that you might see a little bit later on today? If you flip the same coin, a 2-sided coin, we're assuming it lands on a side, like a heads or a tails, okay? If you flip a coin 3 times, how many ways can you get 2 heads? How would you answer that question? What's Jason doing right now? What was he counting?
The possible.
All the possible? Okay, so what are all the possible? You could get heads, heads, heads. Tails, tails, tails. Okay, what's dangerous about doing it like this?
You just keep going.
You might miss things. So is there a systematic way? Is there a systematic way to where you're not just saying like, oh, I think I got them all? Couldn't you say, what if you get a heads first? If you get a heads first, okay, what could happen second? Let's say you get a heads first and a heads second. What could happen third? Okay, and a tails. Or what else could you get with a heads, heads? Okay, do I have like having a heads and a heads, and a tails and or a heads? Okay. How could we then expand that? What if we start with the heads, right? And then what if we have a tails? We could have a heads, tail, heads, or we could have a heads, tails, tails, right? Okay, what else could happen?
No, that's already up. The middle one is where we start with the tails.
So we could start with the tails. And let's say we get a heads next, like we did here, right? What would happen if we got a tails and a heads? We could either get a tails or we could get a... Oh, sorry, tails, heads. So I'm doing the same thing here. I'm like, okay, what if my beginning changes and I get a tails instead, right? Then I could get a heads next, and then, okay, let's say that's true, either a tails or a heads. But then what else could happen? I start with a tails and I get a tails next. So I start with the tails, I get a tails, Then I only have 2 options for the last one, right?
Yeah.
Have I gotten them all?
I think so.
I was like, what if we start with the heads and get a heads? Then we only have 2 options. What if we start with the heads and get a tails? Then we only have 2 options. What if we start with the tails and get a heads? Only 2 options. What if we start with tails, get a tails? 2 options. There is a mathematical way of doing this. Because imagine if I said if you flip a coin 20 times. Okay, but pause. What was the objective?
2 heads.
2 heads. So how many of these have 2 heads?
3. No, 4. 4. Heads.
Ah, but I didn't say at least 2 heads. Careful. So, no. But probability does usually add an extra word, because what Joe said is like, well, you do have 2 heads. You have 3. I mean, you have more than 2. So usually in probability, they add an extra word. They either add exactly, or at least, or at most. So if it was at most, you could get 1, well, technically 0, 1, or 2. If it was at least, you would get either 2 or 3. And if it's exactly, just 2. So if I add the word exactly, now can't we all say there are only 3 ways, right? But question, which one was harder? This one or that one? Depends on your brain, but for some of you guys, like Jason right away said 3. Well,
Yeah.
didn't you flounder a little? No, maybe you did say 3 and you were solid. But for a lot of you guys, this one was harder because this one was easier to think about the numbers 1 through 8 being added to 12. Like your brains more quickly did that than having all of these options of tails and heads. But let me show you a mathematical way for figuring out that there were 8 different options. You ready? And then we could figure out what the 8 different options are. We would know that we weren't missing any. Then we could count up. Because we actually just kind of went blind. And I said, hey, there's a system. Do you trust me? You guys did this time. But aren't you flipping a coin 3 ways? Or 3 times? How many options are there for the first flip? Either heads or tails. How many options are there for the second flip? Heads or tails. How many options for the third flip? Heads or tails. So for the first, for the second, for the third, instead of going blind and just being like, I hope I find them all, we actually could have mathematically figured out that there are 8 different ways of this working out. And instead of going on this awkward like table-y thing, what we could have done instead is we actually could have done a branching where we said, okay, either you get a heads or a tails the first time. And then after you get a heads or a tails, then question, if you get a heads, what could you get next? Heads or tails, heads or tails. And then if you got a heads, what could happen next? Because you're doing 3. A heads or a tails, a heads or a tails, a heads or a tails, and a heads or a tails. How many different options are there? 1, 2, 3, 4, 5, 6, 7, 8. That would have been probably the best system of actually breaking down all the different options without having to like think of a way. But thinking through, okay, I have my first, I have my second, and I have my, oh, doesn't it kind of look like a, anyway. Okay. We're having too much fun now. But you have your first and your second and your third. And in thinking about, okay, how many ways can I get the first 2, and then those 2 have 2, 2 times 2, and then those 2 have 2 and they have 2, so 2 times 2 times 2. Anyway, the math kind of makes sense. Kiddos, what I just showed you is actually something called the fundamental counting principle. And all of this is because it's great if you can hold into your head all the different possible outcomes of a situation, like all the outcomes, and then pick out the ones that you want. Like, what are all the ways of adding the numbers 1 through 8? Okay, which ones add to 12? So you're able to think of, oh, I can add all the numbers 1 through 8. 1 plus 8, 2 plus 7, 3 plus 6, or 1 plus 7, 2 plus 6. Anyway, you can actually think about adding all the numbers and then finding the ones, which ones add to 12? Well, think of all the different ways you can add to 12. Your brain, for most of you, can kind of hold that in, and it wasn't too bad to think about how many ways this could work. It wasn't even that much worse doing this one. But what do you see the next statement is in your notes? But sometimes there are just way too many to count. Way too many to actually like list out all the different possible situations and count up which ones work. So, in order to help us to that end, like you just saw me kind of do with the branching, or like you just saw me do with the blanks, there are some counting principles we're going to see. There are some formulas, and there are some other clues like, hey, can we repeat or not? Are we replacing or not, etc. So let's start off with one of the easy ones that we can count up. Just a little bit different because this time it's not pieces of paper in a box, which we can visualize. Okay, there are papers in a box. We're pulling out. Probably some of us, probably most of us, if not all of us, at some point have had to like pick a number out of a hat or pick a paper out of a box or pick, like, that's something that either we've done or we've seen someone else do it, etc. This one's a little bit harder because what's getting the number now? A computer, and it's just randomly generating. So a program is just spitting out a number, basically. Now they're spitting out numbers 1 to 12, so it's a little bit more abstract, a little bit less a situation we've been in before, but that's okay. Still talking about numbers, which we're fairly used to. If it's spitting out integers 1 through 12, and it says, how many ways can we get an integer that's divisible by 4? Well, can't you guys just think of 4, 8, 12? So in your brains, most of you just thought of, oh, hey, which ones are, oh, that many. Okay, cool, 3 ways. So we're still kind of in the old-fashioned, just like, oh, my brain can hold this, I got it. When you're rolling a die, when you're picking a card out of a deck, when you're picking a number, our brains are usually okay, flipping a coin. But why does the second one get just a little bit harder?
Because there's a lot of integers here that can form some of them.
Yeah. Technically, there's infinitely many integers if you're allowed to use positives and negatives, but we only have the positive numbers 1 through 12, and that's it. Oh my goodness, add, you're killing me. Oh, and I clicked on it. That's great. Go team. Beep, beep. Yeah, I don't know. Don't ask me. Okay, Joe, what's up, bud?
Isn't like there, like in order to form a sum of 9, because there's no 0 in the number series, you can just find all the numbers smaller than 8. Like smaller where you put that 8 times them. Does it work like that?
I like what you're thinking. I don't think all the words that you said necessarily were perfect, but what you're thinking is good. Yeah. Now, what Joe's telling us is basically don't go to 9, 10, 11, or 12. We can discount all of them. No, we discount. We ignore 9, 10, 11, and 12 because all of those would need negative numbers, right? So forget those. Those aren't going to make 9. 9 can't even make 9 because I would need a 0, and I don't have that. So therefore, which ones could make 9? 8, 7, 6, 5, 4, 3, 2, 1, right? However, the numbers spitting out integers, one after the other. So couldn't it spit out 1 and 8, but also spit out 8 and 1? So then we have to go ahead and double it too. It could spit out 2 and 7, 7 and 2. It could spit out 3 and 6, 6 and 3. It could spit out 4 and 5, 5 and 4. But then that's all we have, right? Because, Joe, you need to take the numbers, cut them in half because they're pairs, and then double.
That's why I think like every number is smaller than 9 has to have a pair of that.
Has to have a pair, but like you said 16 first. Careful. Remember, it had to cut in half because you're pairing up, and then there you go. However, not everything's like that. So, not everything is as easy to contain and to think through all the different possible options. Homework's going to have some where you can just kind of count up and think about it, but when it starts to get a little bit more intense, like how many different pairs of letters in the English alphabet are possible? Well, I guess we could write out A through Z and then say, okay, we have that many options for the first letter, and then what's true for the second letter? Well, A could go with any of the 26 letters. B could go with any of the 26 letters. C could go with any of the 26 letters. D could go with any. It's 26 squared. But instead of having to think about the branching or actually write it all out and get all the different pairs, couldn't we just say, well, we have 26 options for the first, and each of those 26 have 26 options for the second? That's what this is saying. As you guys are writing, the fundamental counting principle. If one event can occur M1 different ways, they're just using variables. E is standing for event, M is standing for the number of ways. You might be like, why not N? Well, N gets used for all sorts of stuff, so they went M. That's okay. Think multiple ways. There you go. But then there's a secondary event that can occur in two different ways. If we're needing to put the two together, and if we could put an and as the connector word, we're going to be able to multiply the number of options for the first times the number of options for the second. Or what if you have 3 events, or 4 events, or 10 events, or 12 events? You can multiply all of the different options together. What if I was to say, how many different outfits could you pick out, could you have picked from to wear the one that you're wearing today? Well, let's just assume that you stay within dress code, right? So, we could say, well, I have like, 3 heritage-approved sweatshirts. I have like 5, hopefully at least 5, heritage-approved polos. I have, well, I know uniform bottoms might be a little different. I have 3 heritage-approved ones. I have this many different, let's just say your shoes match with everything. This many different pairs of shoes that I would actually wear to school. This many different pairs of socks that I would wear with the shoes that I would wear to school. Couldn't we just take all the numbers and then multiply them all and say this is how many outfits you had to choose from? Doesn't mean your mind actually thought of all those outfits. Probably just like, whatever. Right? The blessing of uniforms that most of you don't realize. Some of you are excited for college. You get to dress up every day or change your outfit every day. Some of you are like, oh no, I actually have to think about it? To buy new clothes. Anyway, good and bad. But coming back. Mathematically, instead of having to literally do this branching effect where we say, okay, hey, with our heads, there were 2 different options, and each of those 2 different options had 2 different options, and each of those had 2 different options. Then we can count up all the different ways this could work. We could do that with the letters of the alphabet, but it would be gross. We could do that with our outfits, but that would be kind of messy. Bye. So we can just multiply instead. Say, sweet, 26 squared. Anybody find that yet? What's 26 times 26? Something bigger than 625. 676. 625 is 25 times 25. And I didn't have to list a 1. Well, that's nice. Now, I didn't have to list a 1. Now, there is another way of doing it, technically. Some of you might be interested by this. Some of you might not. You could have also made a matrix. How would that work? Because couldn't you have AA and AB and AC and AD? Huh? Does 26 make sense? 26 and 26. It's no different, but Joe, the branching is a lot nicer. Yeah. Okay. License plate numbers. I just wanted to show you the random little like, oh, it's a matrix. But that only works when you have 2 options. As soon as you have 3 or 4, you'd have to do the branching technique. Oh, the fundamental counting? Yeah. There you go. Multiply and multiply. When we're choosing or putting together or compiling, you could even say, like, how many different course schedules are there for you to choose from for next year? Well, how many options do I have for period 1, period 2, period 3, period 4? Or for my Englishes, my maths, my sciences, my histories. Does that make sense? These are different things that we would use the fundamental counting principle for. Or something like compiling a license plate. Really quickly, gives everyone in your group a high five. I have people falling asleep. It's so sad because we're in probability. Are we good? Okay, license plates. Kind of like pairs of letters, but now we're putting together letters and numbers, but ooh, we have some restrictions, at least as far as this example. How many characters, guys, are going to be in these license plates?
4.
How many characters? 6, right? We have 6 different things to fill in, but of those 6, what do we have? Starting off with 2 letters, and then going to? Now, could I start off with all the letters of the alphabet, A through Z, and then I could say, okay, each of those A through Z could go with A through Z for the second? That'd be messy right away. And then each of those A through Z going with A's through Z's, and then that could go with 0s through 9s. Wait, 0s through 9s? Oh, because, yeah, each digit, just a single digit, right? We could think of all the numbers 1 through 9,999, or we could think about them digit by digit, place value by place value. But guys, let's do the math. Let's not do the weird branching. That would take forever. So how many letters could go in the first spot? And there's no restrictions of which letters to use or not use? Who's not allowed? Does that make sense? But they didn't say repetition is not allowed. This isn't necessarily California restrictions. Plus, California license plates don't start with 2 letters. But coming back, with this scenario, 24 options, 24 options. Okay, now let's go to the digits. Once again, we could think about this, all the numbers 1 through 9,999, or we can think digit place by digit place, which will be more helpful when more rules come around. So 0 through 9, how many digits is that? 1 through 9 and an extra 1, so 10. And they said 0 and I aren't allowed, but they didn't say I couldn't use 1 and 0, right? Sorry, O and I. O and I are not allowed, but 1 and 0 seems to be fine. So yeah, all 10 are good. Any other restrictions about the single digits? No. So cool. I have all the numbers technically 0 through 9,999, which would be 10,000. Or you could also think about 10 times 10 times 10, which is also 10,000. So we'd end up with 24 squared. Because that's going to be 576 with 1, 2, 3, 4 different zeros. Good. But what happens if they start being pickier? Now, this is no longer a license plate. They're just going to zoom in. I'm going to zoom in. We're going to zoom in on 3-digit numbers. So for all of this, we're thinking, okay, we're filling 3 digits, which, well, maybe we'll think about digit place value by place value. Maybe we'll think about them just the numbers. For instance, if the leading digit can't be 0, 3-digit numbers, aren't those all the numbers 0 to 999? Because 1,000, well, that's 4 digits. That doesn't work. So how many numbers are here, guys? 1 through 999 plus the 0, so 1,000. But if the leading digit can't be 0, who's been left out? 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 10, 0, 20. All the ones up through 100 are not allowed. So leading digit can't be 0. All the ones 0 to 99, everything from 100 on is good. So how many do I have to take away? So what's 1,000 minus 100? But some of you are like, oh, I don't know if I'd want to do that on my own. Couldn't it be 9 times 10? You can't use 0, but you can use 1 through 9. You can use 0 through 10, 0 through 9, 0. Different ways of doing it. One's very logical, thinking of all the numbers that are possible, and one's using our fundamental counting principle. Now, how about letter B? The leading digit cannot be 0, and no repetition of digits is allowed. Now, some of you might be like, I like this whole logic thing. Leading digit can't be 0. Sweet, I have 900 different options, and no repetition of digits is allowed. So take out 111, take out 222, take out 333, take out 444, take out, but what's the problem? What about 211 and 322 and 575 and oh? So instead, let's not do the counting uppy thing. Let's instead say, okay, so how do we get the leading digit not to be 0? Take all the numbers 1 through 9. 0 is not allowed. He's not allowed to be first. How many were allowed a second ago when repetition was allowed? 10. But if a number just got established in this blank, do I still have 10 options if I can't repeat? I have to take away 1 and say, okay, I know there used to be 10, but as soon as one number gets established, any of the numbers 1 through 9 for my branching technique, as soon as I pick a number, it couldn't have been used the next time. So the 10 becomes a 9, and guess what? This 10 becomes a 2 have been used. And I didn't have to count up any possible numbers. Someone help Lauren out, she's struggling. 9 times 8 is 72. 72 times 9 ends up being? 648. Matthew? Because it tells me. Leading means the very first number. When you say a number 572, the leading digit is the 5. The 2 is like the ending digit. Well, 10 has 2 digits, though. So I'm filling place values. So these are all the numbers 0 through 9, 0 through 9, 0 through 9, except 0 is not allowed. Because when you build, Matthew, give me some random 3-digit number. How'd you do that? You filled the first with a number 0 through 9, the second with a number 0 through 9, and the third with a number 0 through 9. So technically you had 10 different options, and 10 different options as far as numbers that you could have plugged in. So you had 10 times 10 times 10 different options. There are 1,000 different possible 3-digit numbers from 0 to 999. There are 1,000 different 3-digit numbers. But if it says the leading digit can't be 0, we're talking about you would write 10, you would write 20, you would write 76, you would write, we're talking about like all the 2-digit numbers having like a 0 in front. Kind of like you would do, you know, sometimes you add a 0 at the end, it's not really necessary, or at the beginning and it's not really necessary. That's what they're talking about. So no, in your head you're like, it's a 2-digit number. Well, but they're saying like you're filling the blanks. Okay. Didn't it get a little bit trickier in the next one, though? Now, the leading digit can't be 0. And the number must be a multiple of 5. How do you get a multiple of 5? You guys going back to elementary, like, number rules?
5, 0.
It has to end in 5 or 0?
Yeah.
So there are only 2 options for that blank?
Yes.
The ones digit has to be a 5 or a 0, or else it's not going to be a multiple of 5. They said, can't lead with a 0. Okay, fine. So only numbers 1 through 9, 100s, 200s, 300s. But did they tell me anything about that guy?
No, it's just 10.
Yeah, they didn't say anything about no repetition. They didn't tell me about anything special, so I guess anybody's allowed. Okay, cool. So isn't that going to be 180?
Yep.
Now my logical ones, you might like letter D, because you're like, oh, got it. All the numbers 400 to 999. Others of you might be like, ooh, but is that going to be 500, or is that 501, or is that 499, or is that... We could always just do it this way. At least 400, who's allowed to be in this blank? A 4, a 5, a 6, a 7, an 8, or a 9? Don't we only have 6 options? Because 0, 1, 2, and 3 just got discounted. But, any problems with either of those 2 blanks? Oh, I said 500, sorry. 600 or 599 or 601. Oh, I said 5. So some of these could be done as far as thinking logically, and that's okay. That's not wrong. That's not bad. But some of them are going to be more complicated. There's no way we want to add that up. Fundamental counting principle is going to be our guy as far as our ability or our way of dealing with counting up options. Now, permutation. Permutation. Sounds a lot like combination. Permutation has to do with ordering. If I were you, the biggest thing to associate on this page is permutation with order. Order matters. Order is important. Permutation. The order is important. An order of n different elements. It's important if one thing goes first, another thing goes second, another thing goes third, rather than something else going first, something else going second, something else going third. Mm-hmm. So let's think about if you're supposed to, or if you even see the word permutation, and you're like, wait, why are they asking how many permutations? You can replace it with words like arrangements or orders or orderings. Arrangements or orderings. Permutation, those are kind of some synonyms, things that mean the same. How many permutations, how many arrangements, how many orderings of the letters A, B, C, D, E, and F are possible? All right, no big deal. A, B, C, D, E, F. A, C, B, D, E, F. A, C, B, E, D, F. Oh, this is going to be awful. This is going to be awful. Unless Joe is starting to say back there, if you guys are listening, 6 times 5 times 4. Wait, what's he doing? How many, think Scrabble tiles. How many letters do I have to choose from? 6. And do they say I'm allowed to repeat the letters? No. So all I have is 1A, 1B, 1C, 1D, 1E, 1F. So how many could I put first? A through F. But as soon as I choose a beginning letter, how many options do I have for the second letter? And then? Why did Joe, and I stopped him, why did he say, wait, isn't that just? What is that? 1 times 2 times 3 times 4 times 5 times 6. Isn't that 6 factorial, which is the same thing as 720? Oh, sorry. For Calc BC, we kind of memorized some factorials. Not memorized, we just use them a lot, and so you just get used to them. But that's 6. 4 factorial is just 24. 6 times 4. 24 times 5 is 120. 120 times 6 is 720. But why is it a permutation? Because, guys, is it a different arrangement or a different order if you put them this way or the other way or any other switched combination? Combination. Why isn't it called a combination? Why is it called a permutation? Have you ever gotten a combo pizza? Have you ordered on the phone or ordered online or ordered whatever through Uber Eats or whatnot? If you order and if you click, well, let's just say you're not doing one of the ones where you like click the toppings, but you're actually like telling someone. Let's assume you call and you're telling someone what you want. If you say, I want a pepperoni sausage pizza, please. And if they bring you a sausage pepperoni pizza, are you going to be like, it's not what I ordered? Man, don't order pizza from, no. Anyway. Okay, now I didn't say the cheese was like an awkward, oh my goodness. Anyway, pause. Are you really going to call them up and be like, you did not give me what I ordered? No, because it's the same combination. Different permutation, maybe. So you can complain about that. But it's the right combination. No, but I said pepperoni sausage. They gave you a sausage. The toppings are there. Your combo is there. Now, why is this tricky, though? If you do not rig your lockers, what are you going to have to do in a few moments when nutrition comes? Put in your locker combination. But technically, mathematically, a combination says the order doesn't. So as long as you get the right numbers in, you're fine, right? Don't tell a middle schooler that. They're already confused enough at the beginning of the year. But some of you are confused enough when you're like, yeah, I haven't had to put it in all year. Yeah. Then someone comes and spins it. You have to go to the office and be like, oh, I don't know my locker combo. Anyway, coming back. So what should they technically be called? Locker permutations or arrangements or orderings. That's awkward. Okay, permutations. So we have a card for permutations, and tomorrow, if we run out of time, we'll also have a card for combinations. Wait, but we already know combinations. NCR. We were just using it for something different. This one's NPR, not like National Public Radio. Well, there's also a thing. But permutations. Maybe you should put it here. Orderings. Arrangements. Ordering objects. Arranging people. Electing people to office. ASB elections are next week, right? If you have one person that's president, one person that's vice president, if you were to switch who was in each of those offices once they finally get elected, or the current ASB, it would be a different arrangement, a different permutation, and I would call it a different council. So it's not always just taking people and arranging them like a seating chart or like a batting order or like arranging Scrabble tiles on a board. It could also be electing people to offices. But anyway, permutations. Order is important. In general, if you are arranging all n elements, if you're having n and you're arranging all n, if you're having n and you're arranging all n, we could call that from all n, you're arranging all n. That's what this would be. That's what we just did. We had 6 letters and we were arranging all 6. But down here it says, well, you have 6, but maybe you're only choosing 4. Or you have 15 players and you're only choosing 9. So down here I could say 15p9. I could even go ahead and put it into this nice little nifty formula that I could memorize. 15 factorial all over 15 minus 9 factorial, which is 15 factorial all over 8. Nope, 6. That's a struggle. 15 minus 9, bud? 6 factorial. But some of you might not realize what that means until or unless I start showing you, well, you would have 1, 2, 3, 4, 5, 6, 7, 8, 9 different spots to fill, and you have 15 players to choose from, 14 players to choose from, 13, 12, 11, 10, 9, 8, 7. Why doesn't it keep going? Because you're not using all 15 players. Do you see the 6 factorial is missing? So the formula comes out of even just the real-life application in the sense of you have more objects than you're choosing. Well, we have to take away some of the factorial, and we do that by division. Hey, you guys, didn't you find the NPR button in your calculator at some point? Sorry, NCR. Guess what's right by it? NPR. Do you need to know how to use your calculator? Yes. But do you also need to know how to actually do it by hand? I bet I'll have a blank, something to do with the factorial formula, something like the test you saw yesterday for NPR on this 1, 2. So we're done, right? We're actually super, super close. Not too bad, right? Tomorrow we're going to talk about what if some of those things are repeated and combinations. Bye, cool kids. I'll see you later. You totally have enough to start homework. Probably not finished, though. Happy nutrition.